Hey everyone, and welcome to another High Yield Explainer. Today, we're literally conquering your computer science exam with a complete masterclass in data representation. Look, if you want to grab those top marks, understanding exactly how computers handle data under the hood is absolutely essential. So we're going to lock down these exam-critical concepts together, step by step.
Okay, let's dive right into our game plan. In this explainer, we'll cover number system conversions, negative numbers and overflow, binary shifts made simple, the power of hexadecimal, and finally, acing specimen paper questions.
All right, kicking things off with Section 1, Number System Conversions. Getting these foundational mechanics dialed in right out of the gate is absolutely key to earning those high marks. Honestly, if you can confidently translate between these systems, you're already halfway to an A. So here are the big three number systems you need to know intimately. We've got Denary, which is just our standard base 10 system we use every single day. Then there's binary, the base 2 system using only zeros and ones. This is what computers natively process through logic gates. And finally, hexadecimal, the base 16 system. Knowing the fundamental base of each is your starting baseline before we get into the actual math.
So how do we actually do the math? Well, when you need to convert a positive Denary integer into binary, there's this foolproof algorithm called the continuous division method that you should absolutely memorize. It's super simple. You just divide your Denary number by 2, write down the remainder, which, will always be either a 0 or a 1, then divide your new quotient by 2, and repeat until you hit 0. But here's the absolute trick. You must read the remainders from bottom to top to get your final binary number.
Let's actually put that into practice using the number 25. Taking 25 divided by 2 gives us a quotient of 12 with a remainder of 1. Then 12 divided by 2 is 6 with a remainder of 0. We just keep going all the way down until the quotient reaches 0. Then, reading those remainders from the very bottom row up to the top, we get 1, 1, 0, 0, 1, right? So, Denary 25 is exactly binary 1, 1, 0, 0, 1. It's simple, it's repeatable, and it works every single time on test day.
Moving right along to Section 2, Negative Numbers and Overflow.
Now pay super close attention here, because examiners absolutely love to set traps with negative numbers. You see, computers don't have a magical minus sign stored away in their memory registers, so they handle negative integers using a genius method called 2's complement. Lock this 4-step process into your brain right now. Say we have an original binary value of 1000, 1000. First, you find the 1's complement by simply toggling every single bit. So all the 1s become 0s, and all the 0s become 1s, giving us 01110111. Easy enough, right? Then you literally just add 1 to that result, and boom, our final answer, the 2's complement, is 01111000. This is the precise sequence you'll need to demonstrate to represent negative integers.
But what happens when a computer basically bites off more than it can chew? You get an overflow error. The definition of this is strictly high-yield exam vocabulary, so memorize this. An overflow error occurs when a value outside the predefined limit a computer or register can represent or store should be returned. For example, if you're working with an 8-bit register, its absolute max capacity is 255. If your addition results in 256, bam, you've got an overflow error.
To really picture this, you gotta know your bits. The most significant bit, or MSB, is the leftmost bit in a given register. The least significant bit, the LSB, is on the far right. Overflow specifically happens when the sum of that leftmost MSB column produces a carry forward that pushes right past the physical limit of the register. The data literally falls off the edge of the allocated space.
Next up, Section 3, Binary Shifts Made Simple.
I know bitwise operations and binary shifts sound super abstract and intimidating, but I want you to reframe them. Think of them as the computer's built-in quick math hack. Think about it. How do computers multiply or divide rapidly without memorizing times tables like we had to do as kids? Well, they use bitwise operations, mechanically shifting numbers left or right across the register.
Visually, a logical left shift is exactly what it sounds like. You take your binary sequence and physically shove every single bit one spot over to the left. That most significant bit on the far left? It gets completely discarded, tossed out. And to fill the empty space on the right, you just insert a shiny new 0 as the new least significant bit.
The practical effect of this is practically magic. If we take Denary 53 in binary and perform one single logical left shift, the value mathematically jumps to 106. Every single logical left shift perfectly doubles or multiplies by 2 the positive binary integer. And conversely,
A logical right shift divides it by 2. Just remember, any bits shifted completely off the end of the register are permanently lost.
All right, on to Section 4, the power of hexadecimal.
You might be wondering, if computers run natively on binary logic gates, why do we even bother with base 16? Understanding this why is basically a guaranteed 2 to 3 mark question on your paper. Programmers absolutely prefer hexadecimal over long strings of binary machine code for a few big reasons. First, it's just way less prone to human error when typing it out. Second, it's significantly easier for us to read and understand. Third, it is much easier to convert long binary strings directly into hexadecimal than trying to convert them into denary. And finally, it takes up way less screen space. I highly urge you to memorize at least 2 of these points.
Plus, hexadecimal isn't just some classroom theory. It is everywhere in the wild. It's used for color codes in HTML, MAC addresses, IP6 addresses, URL encoding, and assembly language. But it's especially powerful for memory dumps. A memory dump is a hexadecimal view of data pulled directly from RAM, and programmers use it as a massive fault tracing tool for debugging. So, when that exam asks for real-world applications, you've got a whole arsenal of strong examples right here.
Finally, Section 5, acing specimen paper questions.
Okay, theory time is over. Think of me as your expert tutor right now as we do a quick specimen check. We're going to directly apply what we learned to the exact format you'll face on test day. Here's a classic, high-value prompt. Describe what is meant by a MAC address, worth 4 marks. Take a second. Mentally test yourself right now. How many distinct points can you pull from what we just discussed?
So, the secret sauce here is matching your knowledge directly to the marking scheme. To secure all 4 marks effortlessly, you'd write, 1. It's a unique identification of a network device. 2. It's 48 bits long, typically represented in 12 hexadecimal digits. 3. It's a static address set permanently by the manufacturer. And 4. The first part specifically identifies the manufacturer, while the second part is the serial ID. 4 concise points, 4 super easy marks.
Let's look at one final specimen trap. Explain why overflow occurs when 2 binary numbers are added by a computer, worth 2 marks. Do you remember our exact vocabulary definition from earlier? For 2 marks, you always need the overarching rule and the specific context. Point 1. Overflow occurs because the number of bits in the result is greater than the maximum value that can be safely stored in the given register. Point 2. You drop a concrete example. State that an overflow error will unquestionably occur if a calculated value is greater than 255 in an 8-bit register. Providing both the rule and the example is your absolute cheat code for full credit.
Before we wrap up this explainer, I want to leave you with a really fascinating paradox to chew on. What if the very register limits that cause these frustrating overflow errors are actually the secret key to unlocking how we force computers to subtract using only addition? That's exactly the genius of the 2's complement method we explored today, literally using the physical, hard limitations of the hardware to invent a wildly clever mathematical workaround. Keep that in mind as you dive deeper into computer architecture. Good luck with your studies, and I'll catch you in the next explainer.